or PDF. This one. Hello. Okay. Wait. Time? I guess we wait to 9. Okay, I think it's time to start. So I guess any question before we start the review? Although we're going to see what we talked about this class too. Anyway, this is the final review. So the range is actually everything. Obviously, you should still remember how to do Gaussian elimination, etc. But the main part are chapter 4 to chapter 6. So that just goes through what we taught in chapter 4 to chapter 6. It's quite a long time ago we talked about chapter 4. So chapter 4 is about linear transformation. And well, this is a linear transformation. So linear transformation maps a vector from some vector space to a vector in another vector space. So from vector space V to vector space W. And well, it's a mapping, so it's a function, and the function need to satisfy this linear relationship to be called linear transformation. So if you have a linear combination of your vector of your input vector, then the output vector will be the same linear combination. So you have alpha 1 plus beta 2, then you also get alpha 1 plus beta 2 here. Okay, and there are some easy property you can derive for a linear transformation. So you will map 0 to 0, and well, and if you got so we only got 2 terms. So if you have more terms, linear combination, you also get 2 linear combination, and also you get a negation of vector to a negation of vector. Okay, so those are linear transformation, and for linear transformation, we can define a few subsets related to them. So first, there is a kernel. So this is so you make from V to W, and the kernel are those things inside V that will all map to 0 in W. Okay, and the kernel is a subspace. And also there are image and range. So image is defined for some subspace from V. So if you have some subspace in V, and you think about all the things that can be mapped from this S, and that's called the image of S. So L of S here. And then range is just image of everything inside V. Okay. And image and range are also subspace. Okay. So that's 4.1 is basically definition. So we define for the linear transformation. And then we define those spaces that we'll see a lot. So the kernel and the image. The kernel are things that will map to 0, and the image are things that image are things that are made from the set you specify, and they are range. Okay, so we should also have range here. Kernel, image, and we already have So kernel, image, and range. Okay, those are things to remember. Kernel, image, and range. Question so far? And so I guess we can jump ahead a little bit. So now we have seen that the kernel and the range are kernel and range of the when you consider this mapping as a matrix, then kernel and range are pretty useful concept. So if this mapping is defined by a matrix, then kernel is a null space, and so kernel is a null space, and and they are row space. And And so there is a kernel that's a null space, and there are row space of this space that's actually dual to the kernel. Okay. And yeah. So I guess it's better to say so kernel map to a null space, and then range you can kind of think about everything that so there is a orthogonal part to the kernel that will map to everything in the range. Okay, and yeah, we'll see that later. Okay, probably here or a bit later. Anyway, so 4.2.1. Okay, so as we said, now we know linear transformation, but now this is very abstract, and we want to define it in more concrete terms. And what do we find out that is linear transformation actually can be all defined by the matrices. So in terms of this Rn to Rn, we can write this linear transformation in terms of standard basis. So if we think about our so we can think about what this linear transformation map the standard basis vector into. Okay, and so each Ej will get mapped to some vector in Rn as Aj. And we find out that if we just write this matrix A as we listing all those vectors as column vector, so those Aj are what the Ej got mapped into. Okay. And we find out that this matrix will represent how you map from your Rn to Rn. So if you have whatever vector in Rn, and you can just multiply this matrix A on it, and you will find the corresponding matrix in Rn. This is just because the mapping is linear, and so you write X as a linear combination of all those standard basis elements, and then you can then by linearity, remember linearity we have this thing, so we find out that all the mapping of the standard basis element, and X is a linear combination of standard basis element, so the image of X is a linear combination of those image of standard basis elements. Okay, and then you move things around, you find out that that can be represented by L equal to AX, where A is this matrix. That's listing all the columns as the mapping of the standard basis element. Okay, and then we find out that if we don't want to do standard basis, if we so if we are not in Rn and Rm, and we are in arbitrary space and having arbitrary basis, then we can still do similar thing. Okay, so if we express the arbitrary vector v as a coordinate in this basis E, so this is x1 to xn, and then map the result. So LOV as a coordinate in F, so this is y1 to yn. Then we find out that we can still have AX equal Y with we can still have AX equal to Y, but AX equal to Y, but with now our with our AJ being like LOVJ in terms of basis F. Okay. And here we have this here we have this correspondence, so we have V to W, and then we think V has an n-dimensional basis, so we kind of correspond V with this order basis E to Rn, and we correspond F W with, we write everything in W as a m-dimensional vector with this F. Okay, so we turn our small v to we turn our small v in terms of coordinate, kind of the coordinate is like in Rn, and so this Rn to Rn has some mapping y equal to Ax, just like it before, and then you can map things back and forth. Okay, and And finally, then we go back a little bit, we can think about what happens if E and F are basis for actually R and Rm, not just some abstract space. Then we can write this a bit more compactly. So Aj once again, it should be okay. So once again, you should look at the what those basis element got transformed into. But now this sub f thing get a little easier. You can get b minus 1 because that's a whole coordinate transformation between standard basis in Rm and the standard basis Rm and this f basis in of Rm. Okay. Where b is just a listing of those vectors. Okay. And yeah, so here is the summary of the results. So we have a 3 theorem. So we start with Rn to Rm, then we generalize to V to W. Then we go back to a little bit where V and W are Rn and Rm, but we just change the basis for Rn and Rm. Okay? And as you say, so the most important concept is you want to find how the columns of A will be basically how you map the basis element of your starting space. Okay? So here we have Aj equal to L of Ej, and here we change the basis. So Aj is basically L of Vj, but you need to write in coordinate of W, so you write in terms of F. And then finally we have this coordinate in F in more compact form, that's b minus 1. Okay, so that's 4.2. Then 4.3. Okay, and we have E and F. And 4.3 is not too much. So we think about now we have a linear transformation from V to V. So basically a linear operator, if we are mapping into a sense space, then here, then the sense space, then we can choose the same E and F here. And so this is Rn to Rn, and we have a E equal to F here. Then we can think about different E here. Okay, so it's really confusing. So we have an E on this V and an E on this V, and we change to F on this V and F on this V. And we have a different matrix A. And then, so this transformation matrix A will turn into transformation matrix B. And they are just related by this S minus 1 AS, where S is transition matrix from F to E. Okay. From which direction you need to memorize. It's a bit confusing. Okay, but the idea is that you map from, so A will map from V to V, and there's a transition matrix between basis E and basis F. Okay. Actually, what we want is this. So we want what is mapping from V to V in terms of basis F. And so we first transition from F to E, and then we do the we first do a transition from F to E, so we got this S here. Then in basis E, we know how we get how this L operates. So that's you get the HRA, and then we need to map back to this basis F. So we get S minus 1. So everything together is S minus 1 AS. Okay. So in B, then in basis F, this B is you go to S first, then A, then S minus 1. Okay, and yeah, that's 4.3. So if you do transition basis in your, so if you are starting from V and ending in V, then you can pick different bases E and F here, and then this different transition matrix will be S minus 1 AS. And but also a very important concept here is just similarity. So if there exists on S where B equal to S minus 1 AS, then we call A and B similar. And also it's easy to see that if B is similar to A, then A is similar to B. So this is a transitive property. Okay, so that's chapter 4. And then let's go to chapter 5. Chapter 5 is about scalar product or inner product. Okay, and so when we actually teach you about this, we start in R2 and R3, but I think now we can just do the more generalized version. So let's talk about Rn. So in Rn, the inner product is written in this way. So if you have two vector in Rn, x with coordinate x1 to xn and y with coordinate y1 to yn, then the inner product is is you put x as a row vector, y as a column vector, then multiply those vectors together. So multiply them together as a matrix multiplication, then you see that you are multiplying each coordinate, then sum over those products. Okay, so you have x1 y1 plus x2 y2 to x and y. So this is the definition of inner product in Rn. You have two vectors, then you do this product, sum of products over their coordination. Okay, and so inner product is very good. It tells us the geometry on the vector space. Okay, so then the first thing we can define is length. We can define length from inner product. So length is, so we take a square root of it. So if you have a vector, then you inner product it with yourself, then take a square root, then we think it's a length. Okay, because you write a coordinate that's length in R2 and Rn. R2 and R3, so we think that should generalize to Rn. Okay, so this is length, and length of a vector, then you can talk about the distance between two vectors, that's the length of their difference. Okay, and then you can prove okay, so that's the length. Then we can also talk about angle. Okay, so angle between two vectors are defined. Before we define that, we know that we can show that there is a Cauchy-Schwarz inequality for this inner product. So basically, a norm of inner product is less than norm of the first vector times the norm of second vector. Okay. Okay. And from here, then we can define the angle from the inner product, because we know this inner product dividing by norm is something between -1 and 1, so we can think about that as cosine theta. So where theta is the angle between two vectors. Okay. So cosine theta is something between -1 and 1, and then you can do arc cosine to get the theta between 0 and pi. Okay. And also you will now have length, then you can normalize your vector. You can talk about unit vector. So you just divide any vector with its length, then it's divide any vector by its length, then you will get a vector with length 1. Then you can write cosine theta again more completely. So if you take a unit vector associated with x and y, then their inner product of those unit vectors is cosine theta between them. Okay, and okay, so you have an angle, and there's a spatial angle we like, that is pi over 2. Okay. So if a two vector has angle pi over 2 between them, that means cosine theta equals 0 and the inner product is 0, then they are orthogonal. Okay. And sometimes we use this notation to write orthogonal. Okay. And more about this. So with this angle, we can also talk about projection of one vector on another vector. So geometrically, the intuition of this: you have a vector x and you have a vector y, and you want to find some vector along the y direction. That's like that is a projection of x on y. So this vector should satisfy. So x should equal to this u plus another vector z, where u and z are orthogonal. So we see that we need orthogonal to define projection, because by projection we mean x is a projection part plus the orthogonal part. Okay. Okay. And then this u we can find by view trigonometry. So basically u is proportional to y, and its length is x. The length of x times cosine theta, right? That's by the trigonometry. Okay, and the cosine theta we can get from, okay? So the length of u is alpha, that's the length of x times cosine theta. And the cosine theta, as we say, you can get from inner product. So cosine theta is like x dot y divided by xy, and so then everything together you got this, and you can then multiply alpha with a unit vector in y, and you get a projection vector with this complicated formula. Okay, but the important thing to remember here is, if you remember alpha equal to x cosine theta, then you should be able to derive everything here. But obviously, you can also just memorize this result. Okay. Okay. And so that's scalar projection. Okay, and so a few summary 5.1. So we define inner product in Rn is x transpose times y, and it's a sum of all those coordinate product of coordinate, and then we define length as the square root of inner product of itself. Then there is angle, and orthogonal means the angle equal to pi over 2, and there is projection with a complicated formula. Okay. So that's inner product in Rn. Oh, why do we have? Oh, okay. And then we go to then we go to 5.2. Then we now talk about orthogonal spaces. Okay. So now we have two subspace. So x and y are two subspace, and we say they are orthogonal. If everything inside, so you have every pairs pair of vector where x is small x from x, small y in y. So every of those pairs are orthogonal. Then we say x and y are orthogonal. So it's a very strong property. Okay. So those are orthogonal subspace. Okay. So it kind of feel like this. So everything inside this line and everything inside this line they are orthogonal. Okay. And then we have orthogonal complement. So the orthogonal complement of subspace is unique. So if you have whatever subspace, then we can find the orthogonal complement of it. So, and it's written as is y perpendicular. So y perpendicular is everything that's orthogonal to y, and we can show that this y perpendicular is a subspace, and it satisfies a few properties. So basically it's unique, and you take complement, you back to y. Okay. And I guess we can have an example. So a good example here is so we have been keep running those examples. So y equal to say E1, then so in R3, then y complement will be E2. Okay, I should say y equal to span of E1. Okay, so it's easier to write basis. But so y equal to span of E1, then y complement will be span of E2 or E3. Okay, so like this. So you see the complement into R3. Okay, and I guess we can jump a little bit. Okay, never mind. But yeah, but later we will remember. Later we prove that the complement, if you think about their basis element, they really complement to the whole basis. So so you can find the orthogonal basis in y and orthogonal basis in y complement, and then those basis elements listing together will be orthogonal basis for the whole space. And this also means that the number of basis elements here plus the number of basis element here equal to this dimension of your space. Okay. Okay. So the number of basis element here, number of basis element here, they sum to the whole space, and also all the basis element here and all the basis element here are orthogonal. Just by the definition, everything inside it should be orthogonal. Okay. And also y complement back to y. Okay. And then we go a little away to talk about different things. That's fundamental space. So we talk about fundamental subspace of a vector once. Of a matrix once again. And yeah, and then so this is something we talk about in chapter 3 a little bit. So we know that we have a vector, we have a matrix A. Then we can think about the column space and the row space. So column space are the space of are the space spanned by the columns of A, and you will be M-dimensional subspace of Rn. Okay, and Then there is the row space that's spanned by the row vector of A, and because of the if you take an issue about the difference between row vector and the column vector, sometimes we write the row space as a column space of A transpose, okay? Because that's technically more correct. Okay? So there is a column space, then there is a row space, or column space of A transpose. Okay. And then what we want, what we show here is an important theorem. We show that the column space and so this is a column space of A transpose. So basically, a row space of A is orthogonal to the null space of A. Okay, and even stronger. So we have a very strong characterization. So the row space of A is actually the complement of the null space of A, or null space of A is the complement of the row space of A. But as we say, the complement can be, so the complement of complement is the same thing. So we can also say the null space complement is the row space. Okay, so this is a very strong characterization of the very strong characterization of the fundamental space of any matrix, and as we say, it's stronger than the regularity theorem that we proved before. Okay. So it not only says that the dimension of length sum to n, also that everything inside it, everything inside them are also belong to each other. Okay. Okay, and then before we say that, then we get this definition of a direct sum. So direct sum, here is a bit funny. So in this direct sum, we define u and v. Don't need to be orthogonal. But anyway, so we define this direct sum as we define this direct sum space. Okay. So we say if a space is a direct sum, so space W is a direct sum of two subsets U and V, and that means that everything inside W can be written uniquely as, so can and uniquely. So each can and uniquely be written as some U in U and V in V. Okay. Okay. So and I guess the high level idea is that a basis for W can be written as just a union of basis in U and a basis in V. Oh, sorry, I should say this the other way. Oh, yeah, I guess that's correct. Yeah. So you think about basis element for U and basis element for V, and so you just take a union of those basis elements, and it should become a basis for W. Okay. And okay, so but back to this orthogonal complement, and so as we say, we have a few more, quite a few theorems about orthogonal complement. So we show that dimension of the orthogonal complement summing together and then equal to n, and then the direct sum we just talked about, and so Rn equal to the direct sum of any subspace S and its orthogonal complement. Also, complement of complement back to is equal to this S. Okay, and yeah, so you see that, then you think about maybe that's right here. Okay, so then you see that this give a strong characterization of the null subspace of A, and so null subspace of A equal to column of AT complement, and this is about R of A. Okay, so we need to see this null space of A and the row space of A. They have a strong property. So using the first one, we get regularity. Okay, for the yeah. So dimension of this plus dimension of this is equal to Rn, and also they are direct sum to each other. So as you say, so you find also no basis of it and also no basis of it. then you just list those two bases together, then they become orthogonal bases for Rn. And also N is R. This N of A is R of A dual, so R of A dual. And so R of A is also N of A dual from this thing. Oh, not dual, sorry, complement. Okay. And yeah. So that's this thing. So once again, so there is quite a few concepts in 5.2. There are orthogonal subspace, and so just means then there is an orthogonal complement, and then fundamental subspace. So we have a more picture later. Okay, and there is some, and then those three theorems told you about property of orthogonal complement. Okay. And then there is something that we didn't list here, but you can probably find in previous review. That's the algorithm for computing the basis of all the fundamental subspace. I guess there are at least 4 here, but really we probably want 3 most. Okay, so we want how to find the null space of A, and how to find the column space of A, how to find the row space of A. And in chapter 3, we have shown that basically you do Gaussian elimination on A, then you can already find row in the column, and it's also and you can find row in the column, and you do a little more, you can find a null space. Okay. Okay, so we don't have it here, but you can find the previous slides. And then once again from fundamental space. Okay. So our A is mapping from Cn to Cn, and as we said, they are row space and they are null space. So null space is the kernel of A, and basically things are here, then you do nothing. So whatever things in null space by definition, they map by A to 0. So Ax n equals 0. And then then row space will map to column space. Okay. Yeah. And as we know before, so row space it has rank R, and column space also. Row space has dimension R, and the column space has dimension R, and these are equal to rank. And these were shown by rank nullity theorem before. Yeah, this is the same rank. So in this row space and column space, we think A is very nice. A is kind of 1-to-1. So we made from a dimensional space to a dimensional space, and you can kind of find a pure image of it, although we didn't define. Okay, and yeah. So whenever we map something from this Rn, then we can kind of think of it as, so we know the row space and the null space, they direct some into to this 4Rn, right? And so that means that everything in Rn can be written as something in row space plus something in null space, and then something in null space just maps to nothing. Okay, so we have this here. So any vector inside Rn can be written as something in row space plus something in null space, and the null space part just do nothing, always map to 0, and the row space part gets this meaningful mapping to the column space. And then there are these weird spaces that actually get not touched. So I think this is not so important. It's left null space, so you will basically never get touched by it's something orthogonal to the column space you can find, because you have a column space here, then there is also one complement of it. Okay, the important thing are those 3 spaces. So there is a null space, got mapped to 0, and there is a row space, and there is column space. Row space and the column space map between each other. Okay, and then we talk about a bit more of application of those characterization is that we can solve the least square problem. So least square problem is basically we want to solve A is equal to B. But now we ask what happens if this has no solution. Okay, I guess we want to solve A is equal to B from the very beginning, right? This is a linear system, but sometimes this is inconsistent. But we want to find the best solution out of all those inconsistent solutions. So what we do is we consider the residual. So residual is b b minus ax, and we want to minimize this. Okay, but okay, and we want to find some x hat that minimizes the residual rx. Actually, the norm of this rx is a vector. Okay, and then we jump ahead. So I guess we can forget about the derivation and go to the result. The result is we do a lot of derivation and we find out that. So if you want to find a least square solution, what do you want is you want to solve this normal equation. So instead of solving ax equal to b, you multiply at on both sides. So you have atax equal to atb. And we shown that this was solution. Sometimes there is a unique solution, sometimes there is more, but this will have solution. And solution to this equation will be solution to your least square problem. Okay? So this equation you need to memorize. So basically you multiply at on both sides. atax equal to atb. Okay. This is a normal equation. Okay, yeah, as we say, in general it has more than one solution. And so if you look back to the slide, then we say that if A is 4 rank, then this will actually have a unique solution. So you want unique solution when your ATA is 4 rank, ATA is invertible, and if ATA is invertible, you have a unique solution. You just multiply ATA minus 1 to the other side. Okay. But anyway, this is a more general thing. You can solve a normal solution. And also let's see a bit of example that is for this least square problem. A good application is curve fitting. So you have this list of data, xy pair, and you want to say you want to fit it to you want to fit it to a line, then you do this AC equal to y. Okay. Okay. Yeah. Where A is so I guess I should write this once again. So we want so if you want yi equal to c1 c0 plus c1x and c1xi, and then it will become this AC equal to y. So you write this thing together, then it can be written on this matrix where A is the first one is 1, 1, 1 is correspond to all the c0, and then there's the c1, c1xi. You have a c1 and then you have xi here. Okay. And then you can also have a higher dimension one. So if you want to fit to a quadratic curve, then you have those xi squared in your A here, etc. And anyway, so you have AC equal to y, and then you can solve our normal equation and solve the solution. Okay, and so that's 5.3. It's a least square problem where you want to solve ax equal to b when it's inconsistent, and then you find out that you want to solve ATA x equal to ATB, and then you can use it to first B curves. Okay, and then finally, I guess now we're almost finished chapter 5. And then we have 5.4. Then it's a generalization of inner product. So before we have inner product in Rn as is xty. Okay. And but now we define a general inner product that's in arbitrary vector space, and it's just written as this bracket x and y. Okay. And the inner product need to satisfy 3 properties: is greater or equal to 0. Inner product of a vector with itself is greater or equal to 0, and equal to 0 if only if your vector is 0. And xy equal to x inner product with y need to equal to y inner product with x. Also, it's linear on the first on the x part, so x plus beta yz equal to alpha xz plus beta yz. And also 2 and 3 together will show it's a linear in the second argument too. Okay, so that's inner product, and vector space with inner product is called inner product space. Not every vector space is an inner product space, but anyway. So Rn is a good example we have this inner product of Rn defined as this sum of product of coordinate. And but we cannot abstract everything, so we have this abstract inner product, then we can do this Rn thing again. So we can once again define length. Oh, I have a typo. So this should be inner product length of x should be inner product of x with itself. Okay, and so x, let's just rewrite square root inner product x is the length of x, and then you have an angle. Angle with cosine theta defined by inner product with xy dividing length x, length y. And then orthogonal just means inner product with 0. And then you can do projection once again. Okay, projection. Yeah. Okay, so that's the inner product and the geometry associated with inner product. You have length and angle. But actually, you can now we have this weird concept is you can so the inner product geometry has length and angle. But actually, you can have something in between. So there can be space that you only define length, but you don't define angle. Okay? So you only define length, then you need to define unknown. Okay? So length of a vector. So length of a vector is just whatever function that map your vector to a real number, and you need to satisfy three things. So you want length to be positive, length is greater or equal to 0. And equal to 0 means your vector is 0. And also I want the length to be respect to a linear structure of a linear space. So if you multiply by alpha, then the length can multiply by alpha absolute value. And also you want to satisfy triangle inequality. So the sum of two vectors is length less than the sum of the length. So length of v plus w should always smaller or equal to length of v plus length of w. Okay. So if some function satisfy those three things, then it's known. Okay, so it will tell you the length of a vector. And so this length defined from the inner product is known, but there are also other known. And a very useful set is p known of r-dimensional vector, of an n-dimensional vector. So with the usual length we have is the 2 known. So it's you square every square, you take the absolute square of every coordinate, and summing them you take square root. But you can generalize it to p known, so you can have this absolute value to some p's power for whatever p. I guess positive real p, and you sum it together and take p's root, and that's called p known. So for any positive real p, this will be a known. And but actually there are three p that people use most often. It's a 2 known, and then there is 1 known. That's just so p equal to 1. That is just the sum of absolute values. And also there is infinity known. So you think about what happens when you take p to infinity. Then only the biggest number will dominate this summation, because you go to infinity, and so that's a mix of your coordinate. Okay. And yeah, so 1 known, 2 known, and infinity known. And also, so that's for vector, and also you can kind of think your any Rn by n matrix as a vector, and then you just list them as all the coordinate. Then the 2 known is called the forbiddance known. So you just have the sum of the element square and sum of the element square and taking square root. Okay. So that's the 2 known of all the elements. That's the forbiddance known of the of your matrix. And but later we see that forbiddance known is very interesting. It's also the 2 known of the it's also the 2 known in terms of the singular values, right? So if you still remember the singular values, there are some way to the kind of a diagonalization of the matrix. Okay? So if you sum your singular value together and taking a square root, that's also your forbiddance known. So Thus, the spatial for two known, I think only in two known is this, is a two known in singular value and two known in element is the set. Okay, so that's interesting. But anyway, here is a checklist. So we define general inner product and general known. So inner product, they need to satisfy these three structure and can give you geometry on your vector space. And then we can define known, they only need to satisfy these three things. Okay, and for business known, they are nice. Okay, 15 minutes, we are a little slower. And okay, then 5.5. We talk about orthogonal set. So orthogonal set means everything be. So a set of vectors where each pair between them are orthogonal, then it's called the orthogonal set. And if you are orthogonal, then you are linear independent. So orthogonal is a stronger condition. So we think about orthogonal like this: the two vectors, the angle between them are 90 degrees, and the linear independent is weaker. Linear independent just means that those two vectors they have some angle between them. Okay, and so every pair have those kind of things. Then it's it's a bit more, but anyway. So that's orthogonal and linear independent, and then you can also have orthonormal. That means everything is orthogonal and it has length 1 and it's orthonormal. For example, is U1, E2, E3 are orthonormal. And then if you are orthonormal and you are basis, then you are called the orthonormal basis. Okay, and orthonormal bases are very nice. You can calculate a lot of their property easily. So say if you want to calculate the coordinate of on your orthonormal basis, then you only need to take an inner product of your vector with the corresponding basis element. Okay, and so orthonormal basis is really like standard basis. Yeah, so you can get a base because basically the coordinate of each element doesn't affect the coordinate of the other one. Okay, that's a bit weird thing to say, but anyway. Yeah. So you can find this coordinate vector by taking inner product, and also if you want to take the inner product of two vectors, then you can just take this basically the inner product between those two coordinate vectors. Okay, and and the length square is the sum of coordinate numbers squares, and yeah. Okay, yeah, that's the possible formula. Okay, yeah, so that's orthogonal basis. They are very nice, and also there is orthogonal matrix basically transform between orthogonal basis. So orthogonal matrix is you list orthogonal basis together. So if this matrix is n by n matrix and all your column vectors are orthonormal, then it's called the orthogonal matrix. And orthogonal matrix has a very nice property. So for example, you take a transpose and tiny itself, then equal to identity. So it means the transpose is -1 of your orthogonal matrix. And so all the properties are here. So definition, column vectors are orthogonal basis. Then transpose times itself equal to identity. And that means all the row vectors also form an orthogonal basis. And also they are very nice because they didn't change the length. So if you take doesn't change the length and the angle of your vector space. So you multiply a vector by a orthogonal matrix, the length is still the same, and you multiply x and y both by this q, and the inner product doesn't change. Okay. And also a bit of I guess the application of orthogonal basis is you can find a projection onto a subspace. Okay. So if you have orthogonal basis for your subspace on subspace S, and you have whatever vector x, and you want to find a projection, then you can just find the P as is Ci Xi. So some linear combination of your orthogonal basis in S, where the Ci is this, once again, this coordination. Okay. And this is true because in next because with if we have orthogonal basis for S, then we can also always extend this to orthogonal basis of everything by thinking about there is S perpendicular and S perpendicular has another orthogonal basis, and so you can you can always decompose your X into this S part and S perpendicular part, and then the S part will just be this formula. Okay, so that's for 5.5. Then 5.6. Then okay, we're a little slower. Okay. Anyway, 5.6. Then we talk about grand streaming process, and basically this says that any any finite dimensional vector space we can construct an orthogonal basis, and so this is a very constructive process where we say we take whatever basis, then we can turn it, we can get the orthogonal basis out of it. So basically we keep getting, so we start from x1 to xn, and so we start from x1 to xn, and we construct u1 to u1 by keep normalizing things, and when we add something extra, so say we already have some u1, u2 span your x1, x2, then we have x3, then we can do the projection we just said, and we find the thing of x3 that's perpendicular to this u1, u2, and we'll normalize this will become u3, and so u1, u2, u3 will span x1, x2, x3, etc. Then we add the x4. Okay, so we keep doing this, and then this process will give you also normal basis. Okay, and yeah, so this is very nice. We use this to prove the thing before once again. So those things about SN's dual, you can look more clearly from this grand streaming process. So grand streaming process tells you that you always have orthogonal basis for your finite dimensional space. Okay, it's very cool. Okay, then finally we go to chapter 6. So chapter 6, we go to quite different topic. It's eigenvalue and eigenvector. And so start with focusing on n by n matrix. So by n matrix, we can find eigenvector such that ax equal to lambda x, where lambda is just a scalar. And so this x is called the eigenvector, and the lambda is called the eigenvalue. Okay. And just from that equation, then you can move things around. So ax equal to lambda x, then a minus lambda x equals 0. That means the null space of a minus lambda I not equal to 0. And that means this is singular, and that means determinant of a equals 0. Okay. And so from all the way here, then we can solve the determinant a minus lambda I. We can solve this for lambda, and can solve this for lambda. Then once we get this lambda here, then we use this. Then we solve the null space of associated with lambda to get your vector x. Or actually, I guess more likely you use the wrong equation b. Okay. So the two equations you run is you want to find lambda and x, then you solve this for lambda, and then you go back, and you do this for x. Okay. Okay. So that's a quick summary of how you find eigenvalue and eigenvector. And let me talk about complex eigenvalue and complex eigenvector. And because our matrix is real, so the complex eigenvalue and the complex eigenvector have a strong property where they always have the conjugate pairs. So you have some lambda and z being, if you have some lambda and z being eigenvalue eigenvector pair, then lambda bar and z bar are also going to be eigenvalue eigenvector pair of your matrix A, where bar means complete conjugation. So it means you put a -1 in over your I. Okay, and so that's the complex eigenvalue, and more property on eigenvalues. So eigenvalue, when you solve this equation, there are going to be n roots of them. So you will have n eigenvalues, and you have n eigenvalue, and you can derive that the determinant of A will equal to a product of eigenvalue, and the trace of A which is the sum of this diagonal element is the sum of eigenvalue. Okay, so that's very nice. And also, we show that if A and B are similar matrix, then their eigenvalues are going to be the same. Okay, yeah. So yeah, whatever your similar transformation S is, A and B are similar, then A and B will have the same eigenvalues, although the eigenvectors might be different. Okay, so here's the summary. We have the eigenvalue, eigenvector equation, and complex eigenvalues determine equal to product, trace equal to sum, and similar you have the same eigenvalue. And the next thing is diagonalization. So diagonalization means we want to find a similar matrix that's diagonal. Or in other way, we want to write A equal to some x and a diagonal matrix and x and minus 1. So x is some non-zero matrix, so you can have x minus 1. Okay? And there are two theorems. We say that basically if you want to be diagonalizable, then you want n linear independent eigenvector. And one way it's possible is if all eigenvalues are different, then all your eigenvector will be linear independent. Okay? And if n linear independent eigenvector, then basically you can write this big X as listing all your eigenvectors together, then this big X will diagonalize your matrix. Okay? So because you can show Ax equal to xt, and as long as your X has the inverse 1, then you will have x minus 1 Ax equal to d. Okay? And so if your eigenvectors eigenvalues are all different, then it's very nice. But if your eigenvalues are the same, then sometimes your matrix can be defective. That means you don't have a linear independent eigenvector. For example, a good example is this. So you have your eigenvalue 1 has 2 multiplicity, but you only have 1 eigenvector. Okay. And so that's the difference between geometric multiplicity and algebraic multiplicity. So algebraic multiplicity is you solve for the determinant A minus lambda I, and you always got n roots. But some of the roots are the same, and some of the same roots don't give you enough linear independent eigenvectors. Okay. And also something we skipped, that is if your diagonalization, then it's very easy to calculate A to the kth power. Basically, you did take this D to the kth power. Okay. And so that's diagonalizable. And then we talk about a matrix that's very easy to diagonalize, or set of matrix. That's the symmetric matrix. Okay. So so we say a real symmetric matrix, they are always diagonalizable, and not only diagonalizable, they can be diagonalized by orthogonal matrix U. Okay, so this X will be orthogonal, and that basically means all the eigenvectors can be, you can find the orthonormal set of eigenvectors. Okay, and so that's about eigenvectors. So the eigenvectors of A are also normal to each other, and also all the eigenvalues are real. Okay. I guess talking about eigenvector being orthogonal is a little weird, because sometimes so here you can still have a bit tricky thing. So let's write this very quickly here. So a good symmetric matrix, so you can still have this multiplicity, right? So symmetric matrix can still have a multiplicity. So say A equal to just 1, 0, 0, 1. So everything will be eigenvector of A, because Ax equal to x for x. Okay? And so you can still have multiplicity for your symmetric matrix. And when you have multiplicity, that means this multiplicity is, you see that this thing will define will define some subspace. So for example, this is a 2-dimensional subspace with this multiplicity. So basically, everything inside this 2-dimensional subspace is eigenvector to A. Okay? And then when we want to find the orthonormal basis for this U, then you just find whatever orthonormal basis in this 2-dimensional space. You can find anything. Okay. And anyway, that's symmetric matrix. And then let's see when we talk about is this singular value decomposition. So we say that for any, so now we go away from n by n matrix. We talk about any n by n matrix. Then any n by n matrix, we can write it as this singular value decomposition U sigma Vt. And once again, sigma is orthogonal, but now U and V can be different, but they need to be orthogonal. So U is orthogonal matrix, sigma is diagonal, and V is orthogonal matrix. And now the sigma we can have is element all positive and listing from biggest one to the smallest one. So sigmas are called singular values, and this is called singular value decomposition. And the singular value decomposition can be calculated from this ATA and AAT. So ATA and AAT, they are symmetric matrix, so you can just use this orthogonal diagonalization. And so if you diagonalize ATA, you will find the V, and this lambda 1 basically correspond to sigma. And if you diagonalize the AAT, you can find the U. Okay. And so here is the example, but we don't have time to jump through. So, but I guess let's go to a checklist. So if you want this, then what we do is we diagonalize the ATA, and you can find sigma V. And I guess you can also diagonalize the AAT to find U, but in our example, we have a quicker way. So we can just, so once you find this sigma and the Vt, then you can just multiply the V on your A, and you will find your U. Okay, that's a bit faster. Okay, and yeah, that's because ATA is V sigma square Vt. So you diagonalize it, and the eigenvectors it will give you V, and the eigenvalues you taking square root, you become sigma. Okay, and singular values are unique, but UV are not. And finally, the PF forbidden known thing we talk about. So forbidden known is also the two known of the singular values. And yeah, so here's the important thing about finding SVT. So you can find this V for diagonalizing ATA, and finding U by diagonalizing AAT. And one more thing is, this here is the number of, I guess maybe, yeah. So number of non-zero singular values, non-zero sigma I equal to rank. Okay, sorry for overtime, but that's the quick review of everything we talk about in this half semester. And hopefully, I guess I will. So we didn't have homework for 5.6.4 and 6.5, but I guess we'll put a few questions with solutions so you can prepare a little bit. Okay, so yeah, good luck on your final on Monday.